Thank you everyone for joining this session. I'm very pleased to actually present this talk here at Scalar. It's my first online conference, so I'm a bit stressed. I guess you can see this. Sorry for that. So I want to thank all the people, all the team organizing the conference, and you, Martin and Marta. So what we'll talk today is I will give you tips. I'll give you tips about writing functional code that doesn't need to be slow or doesn't need to be unsafe. What I'm trying to talk about is a true story. It's something that we really had in prediction, and the problem we faced are a real problem we had, something that was kind of complicated, and the solutions that I give to you in the talk are the solutions we implemented in production. So a big thank you just before starting. So the slides are done using Scala.js. So I want to thank all the people involved in Scala.js because it's great, and I love doing my work, my slides in Scala.js. So who am I, and why am I describing myself? So the reason I'm telling you this is because I want to give you context. So I've always loved math and computer science, and using both at the same time. I've been many things: researcher, teacher, and backend developers, and recently data engineer. So I'm not like the regular functional programming guy who have only done functional programming and things. Actually, I started with BASIC and then C, and I love C a lot. And when I started functional programming 20 years ago, I started with Camel, and I was, that's ridiculous, that's unproductive. I want my statements work, and I mutate things. And so, of course, in the Camel you can mutate things, but it's kind of clumsy and it's not made for that. So it's like, oh, I have to use this. Of course, it was not because of Camel. Yeah, it was because of the new paradigm, functional programming. And at the time, I was my brain was very focused about imperative programming. A few years later, I switched to Haskell, and then so this is what FP is capable of. Without objects that I didn't know at the time. Again, a few years later, then I switched to Java, and I kind of love Java, actually. What I really love is object-oriented programming. I love its concepts. I love what is built upon. But I had a problem. My types were not tweetable anymore. So we have, at that time it was 140 characters, and my types were longer than that. So what could I do in an environment where I need to use Java and I like functional programming and object-oriented programming? Then Scala. And since then, I use Scala and I love it. And during the talk, you'll see why. So all of this made me do what we did in the experiment. So the context. The project we were working on was logistics. I hope you see the video. For those having troubles, the slides are online if you have copied the link in the first slide. So logistics is about moving goods from somewhere to somewhere. And we were working for one of the big players of the industry. And what the problem is this. We want to transfer goods from a place A to a place Z. There are many routes possible. The kind of route, the routes may differ on the price, or how long will it take to actually transfer the goods, and if there are some issues in the route. So what they call a route is made of some legs. What you see here is 5 routes, all going from A to Z. The route 1 is going from A to P using the first line, so the line 1 in red, and then from P to Z using the line 5. It's kind of the same thing as Subway or any public transportation system. The problem is we have many routes, and the lines are, you can take a line from somewhere to somewhere, but all the routes don't go from the same depart to the same arrival. Like if you take the line 4 in route 2 and 3, in route 2 it goes from A to J, and in route 3 it goes through A to M. The problem is there is some perturbations on the route. In the real situation we faced is the client actually was booking some places in the ships, and so he wants to know if it has enough space booked for the whole journey from A to G. So the problem is we have all these routes, and we want to know if a route is perturbed or not. And so what you see here in yellow with the little I is if the route from the depart to the stop is perturbed. So on the right, you see like a leg is going from A to B, and a perturbed leg is from A to B, but there is some problem. The problem may be it might be complicated to go into this zone, or it may take longer than usual, or there might be some complication. What is a journey is just a sequence of legs, and a perturbed journey is a journey where something goes wrong. So, the domain. Modeling in Scala is not that much difficult. We have a leg, it's a line going from somewhere to somewhere. A journey is a list of legs, and we want to enrich the journey with a Boolean saying whether or not each leg is perturbed or not. So what you see on the right, if you see my mouse, this is a leg, this is a journey from A, B to C with the line 4 and line 5. And this is a perturbed journey where the Boolean here says false. 4 is not perturbed, but 5 is. And so this is the domain. To know if a leg is perturbed, we have to call an API. And the API we want, the one that would be the best for us, is kind of the hypothetical one. We want a function, is leg perturbed, taking a leg and returning a Boolean saying whether or not this leg is perturbed. So if we have this information for each leg, so doing a simple map, we can add it to any journey, a journey being a list of legs. And for all the journeys, this is again just a map. So a map with effect, a traverse. But anyway, this is very simple. We just call this function on every leg. This is the API we want because it's simple and it corresponds exactly to the domain we have. Unfortunately, that's not the API we have. What we actually have is a batch API, where we give a list of lines. So remember that the leg is a line, but from somewhere to somewhere. And in the batch API, so the one that the client really has to offer us, we can't say just from there to here. What it says is, you give me a list of lines, and I'll give you all the stops where there is a problem. If, for example, if I want to ask the API, give me the situation on lines 1, 2, and 3, the API can return me, okay, for line 1, there is a problem in stop E and in stop J. But on line 2, there is a problem in stop C, and there is no problem on line 3. So you see there is a mismatch between what we want and what we have. So, of course, there's benefits and drawbacks, and it's not silly for the client to have this API. Why? So the benefits of the API we want is it's very simple for the business logic code. We have a leg, and for each leg we want Boolean. So we have directly this call, and we want this one. but it makes a poor implementation because we would have to call, because the same leg can be used by many routes, and actually the same line can be used by many routes. So if we just perform the call to the batch API for each leg, the performance will be dramatic. On the opposite side, doing all the calls in one batch call to the API, it's very fast regarding the implementation. But then we move all the complexity of handling all this batching stuff in the business code. Obviously, that's something we didn't want. So in the example, you see line 4 here is repeated in the 2 routes. And we want to call the API only one time on line 4, and no 2 times. So that's a problem. So my first tip that I give to you is when you have this situation where you have like something that is simple, slow, and something that is fast but complex, don't choose, take both. What it means is you can actually split, instead of having one abstraction and one implementation, you can split the 2. And what you have is you refer to the business code a very simple abstraction. So actually the one we wanted from the beginning. So what we will offer to the business code is a pleasant facade. It's just this function is perturbed, the leg, and the Boolean. And the auto batch is the magic monad that does the trick. And what we want to be able to is to run this magic monad to return an IO, like something usual, like Zayo or Katz effect. What we want is to the magic monad auto batch to magically make things efficient for us. So what we wanted to do in the background is to call the batch API. So what you see here is the code we want and the one we want. What will do this auto batch monad? It will collect all the calls, all the calls to the API we want, the isLeg perturb. It will collect all the calls, translate them into a single code to the batch API, and then replace in our code every unitary call by the response from the batch API. So we collect everything, we make one single request, and with the response containing all the individual response, then we replace back, and so it is a system of fetching and delivery. And then we loop this task until there's no more call to be made. And this is completely magic. So the second tip I want to give you is write your own dedicated abstractions, because very simple, interesting thing, and Scala is a powerful language. That's something we can do is you can model your own abstractions. So provide your business code the simplest possible abstraction it needs. So what do we need in this case? We need the function isLeg perturbed. That's the thing we need. And everything that you see around, like a new type auto batch, it's because we need to give it a name. So we create a new type, but that's the abstraction. And we want it to be a monad because we want to do computations and we want it to be simple. But the real stuff that makes this possible is we want this function, the isLeg perturbed. So this is the abstraction. All the rest is just to make life easy. The third tip is write your own dedicated data types. One of the problems we had is we couldn't just take the implementation of free monads in various libraries because we wanted to collect things. Maybe we could have doing some tweaking. But the thing is, if you write your own dedicated data types, then it will be tailored to your needs. And that's what matters. So once you've done your abstraction, that it really fits your business code, then you have to write your dedicated data type to provide the implementation and okay, this is the thing where I want to do it. So in our case, what is the data type? What is the magical data batch? We just replaced the call to the illusionary unitary call, so the one that doesn't exist. It's just a case class. It's a case class, and we store the leg, and then that's where the magic happens. And we also added all the case classes to make it a monad, but not a regular free monad thing, just the one that is tailored to a need. And okay. So the difference between abstraction and implementation is very important. Abstract does not mean general. That's something I see very often, but it's not. Abstract means without irrelevant details. So it means that all the details that do not need to be in your business code actually just hide it from your abstraction. Abstraction is like just a wheel, and there's something just behind. But what you want is a simple interface, having all the control you need, but not the dirty implementation stuff, like all the injectors functions or all the complex machinery of the car is actually running. Your data type is not the abstraction, it's the implementation. The trait is the abstraction. So like the abstraction is the interface and the implementation is the real class thing. So you provide your public API and you provide a private implementation. So that's one of the reasons I told you I love the principle of object-oriented programming, and encapsulation is just that. So tips number 4, use smart constructors. The thing is, we want your code to be fast. So we want to provide, we want to optimize the codes we are doing the earlier possible. For example, in this case, we have the app of the applicative monad, and we realize that if we have a pure in both sides, so into the FF and the FA, then there's no need to actually build a case class app. We can just directly apply the function to the argument. So bypassing completely the need to build the complex structures and then realizing in the evaluator that, oh, we can actually perform it directly. No, everything that can be done directly is done directly. What they can do is they can enforce properties, they can perform optimization. So don't build complex structures just to realize that they're too complex. If you can simplify things early, do simplify things early. So how the auto batch worked? Actually, with lots of magic. There are lots of magic, and it's not all of it is not the subject of the talk. So to convince you that it's not that simple, it's actually a monad transformer. So more complicated than I presented you. It's lots of GADT. It's a kind of free monad, but not a regular one. And it's also free applicative, and that's very important to be able to parallelize. And so, but the thing is, it's designed exactly for a need. And our need is to maximize parallel computation, because we want to have the more opportunities we have to catch unitary calls, the better it is. And we want to perform optimization as early as possible. So that's the same. So we did the work, and okay, that's good stuff, and I was very pleased to have the occasion to work on the programming I like. And so when we released this feature, we were very happy. So we released to production, there was party time, everything was fine. And then the problem is we had some timeouts. And of course, the client was not very happy about that. When I told you to do some optimizations, actually, it's very important that optimizations really do save some time. In order to avoid unnecessary computations, then I had in the code a test doing, okay, if I don't need to do this computation, I just don't do it. The problem is the test to realize if I need to do some computation was much more time consuming than the actual computation it saves us from. So we're at the problem where the optimization was much slower than the actual code. That's a kind of silly thing, but that's why my next tip is you need to profile on production data. What we did was profiling on the testing data, and the production data was a bit more complex and had patterns that we had not considered during the test. So profile and production data. There are a lot of profilers, and use the one that you like the most, but do some profiling. And that's seeing the profiler and seeing the results of profiling on production data that we realized that actually the thing that was consuming so much time was the optimization. That's silly, but yeah, it happens. So we fix this. And we say, okay, so now we fixed the problem. Okay, that's our fault. We're sorry. And then everything works. Just we forgot one simple thing, a knowledge by the wise Edward Met. Like that said, that monads in Scalar for us to be either slow, beautiful lining, or they don't scale. We were not slow, so we were just not scaling enough. And what we had is stack overflows. So the problem with stack overflows, that's a massive problem actually, because when some stack overflow happen in the JVM, it stops the server. And so the client doesn't know why the requests that operators are making are just failing. And for them, it's just random. Because you are an operator, you perform an operation on the system, and then it was fine. You perform the same operation again, and then it just breaks. And you say, okay, which just why? Because someone else actually made a request that generated a Stack Overflow. The server just crashed, and so your request cannot be handled. And if really I have an advice to give to you is avoid Stack Overflows the more you can. They're just dramatic, and we had this problem for quite some time. We actually fixed this issue actually quite fast every time, but having the server to completely crash and the client to don't understand what really is happening was a stressful situation for all of the people involved in it. So what's the problem? We love functional programming, and we are not in OCaml or in Haskell. OCaml has something called tail-call optimization, and Haskell has the same thing. But not Scala, and it's not the fault of Scala, actually. It's the fault of the JVM that just say, okay, we don't mind. So what's the problem? The problem is, as I told you, all our tests were green. But the server was randomly crashing. Actually, the random was like this function. A very simple function, like take an integer, n, and I return 1 added by itself n times. So it returns n2. If I call it on 39,205, then I have the result. Just functions correctly. I mean, who will test with bigger number than that anyway? But if I test on just one more, then it's Stack Overflow. Obviously, it depends on the configuration, it depends on the context, it depends on what's in the stack before. So that's why the randomness of these crashes. Okay, so how can we fix this? To fix this, we say, okay, we have learned a magical technique. we want to have all our functions to be tail-recursive. And how can we make all functions tail-recursive? Actually, not all functions are. If you take the function here, so the one with f, it's not tail-recursive. And if you try to do the tail-rec, then it just won't work, because Scala will say, no, this call to f is not in tail-rec position. But we have learned that we can transform any function to a function that is tail-rec via a CPS transformation. So CPS stands for continuation passing style. And what's the idea? The idea is every time you're calling the function, you pass the function a continuation to do what you have to do next. So let's view this. What you see on the top is the function f. And at the bottom is the function f transform, fcps. It takes the same number n, but the bottom version takes a k, that's a function, saying what has to be done on the result. So if here. So on 1, if the result is 1, what do I need to do with the result? And remember that k is what to do next. The thing I have to do next is calling k, because k is what to do next. Okay, that's fine. But if I call f in here, then before k, that is the end of the what to do next, I have to add the result of f by n. So between the return of f and calling k, that is the rest of the computation, so what will have to be done after the return of FCPS, what do I need to do? So I call FCPS with n minus 1, like in the top version, and I check the result. The result is error, but before calling k, I actually call k on n plus r, which gives exactly what we had before. And so it makes our function tail-recursive. And so we're happy with that. So great, but no. And why no? Your function is tail-rec. Actually, it's much more complex than that. So our function is tail-recursive. That's correct. That's clearly correct. And if I make the function lazy by not returning directly the call to k1, but deferring it, making later, then we see that we can compute actually the call to k. So it works. So the function calling fps lazy, it actually works. But the problem is in the function k. And because we are composing functions, we are making our function so large that that's the composition of functions inside k that is not recursive. And that's really the machine that just laughing at us. Okay, so now what do we have? We have a tail-rec function. But what we have is we cannot compose the k function like we do just here, like composing k and creating a new k just there. What we have to do is using the tips number 7, defunctionalization. Okay, it sounds very difficult, and actually it is, but I kind of give you the idea. So what you see on the left is the version we start from. We start with the FCPS function, so the one that we transformed just before. And we have to locate all the creations of the k argument that we do. So what arguments are we providing to FCPS? So here we provide FCPS with the argument 3, with this argument, like 100,000. And as k, we give the argument the identity function. So one of the possible k value is the identity function. The second time we are calling FCPS. That's with the function R that gives k of n plus r. That's the second creation. So based on this, we will design a data type to represent this function. Because actually, not every function, k is not every possible function. K is some possible functions that's made of the identity function and this composition. And we have also to locate all the calls to k. So we're calling k here, k of 1. And we are calling k here, k of n plus r. And what we will do is transform this function type from int to int, but actually the real values of k will be much more smaller set, into a data type. So the data type, we call it k, with a big K. And then we will give a name to every creation that we have. So the identity function, that we will call ID, and the function that you see here, r done k of n plus r, we will give the name next key, because that's the next k. Okay, what will we need? We need to keep the value k and keep the value n, because if we don't have neither key nor n, we will not be able to compute k of n plus r. Obviously, a function can be created, but can also be called. So we need something to call this function and simulate a function call. We will call this interpreter called k for calling k. It will take the continuation, c, of that k, and the argument, because actually we're simulating function from int to int, so we take the int, and we give back a int. If we have the identity function, and we give it the argument r, what is the result? The result is r, normal. And if it is the next k case, so representing the function r to k of n plus r, then we call k on r plus r. But because k itself is a data type k, then we interpret also call k. So so the function FPPS, what it becomes is fdefn, where every call to the function k is replaced by interpreting the data type k, and every creation of a function k is replaced by creating a value of the data type k. So when we start by giving the identity function. Here we give the identity object of the trait k. And when we want to create a new continuation, here what we give is next k. And when we want to call it, we call it with call k of k1, and here call k of k n plus r. And then we thought it was enough. Okay, it was complex. We had to do CPS transformation. We had to do defunctionalization. It was hard. It was dirty. And then we said, okay, we learned our lesson, but is it enough? So what we have is we started from the function Fibonacci. Like for if I apply the Fibonacci to this, what will we have? So we take Fibonacci, and this is the regular function. If n is lesser than 0, I return 1. Otherwise, I return Fibonacci of n minus 1 plus Fibonacci of n minus 2. And I will call it on a big number. If I apply continuations and defunctionalization, what I have is this. So what you see is my function is tail-rec. That's the premise I'm giving you, because otherwise StackOverflow would raise. So this is the continuation data type, representing all the continuations involved in the computation, and the interpreter, because the continuation will still be a function from int to int, so you interpret this data type as a function from int to int. And as you can see, it starts to be more complex, but it's just all mechanical. Okay, so then, is it enough? No, it's not. Actually, just imagine it was the third time that we had a Stack Overflow in just a few days in the stack. So let me tell you, the client was not happy at all. So it was very complicated. And so, but now what's the problem actually? I mean, another problem, because there are many problems. The problem is mutual recursion. And I want to tell you, I'm not happy at all about the JVM rejecting to implement TCO, and I want them to implement this, because it's just so frustrating. So what Scala does and what Scala does not, because it just cannot. If you have a function like the function f here that just calls itself, actually it will call itself indefinitely, but the thing is, will it fail? And actually it won't fail, because the developers doing Scalar, they're smart, and so they implemented a code transformation that transformed every tail-recursive function into a while loop. And so that's what the tail-rec annotation is, what it is ensuring. It ensures that the compiler really transforms the function into a while loop. But what will happen if actually we have two functions, like G1 and G2, and each function is calling the other one? G1 is calling G2, and G2 is calling G1. Just let's try. And it will fail on the Stack Overflow. But just why? I mean, just what we had is we had to transform into CPS, we had to defunctionalize, and now we have a third thing that is the mutual recursion. So what can we do now? What we can do is trampolining. So what is trampolining? The thing is, to avoid growing the stack more and more, what we need to do is to make the call to G1 or G2 to actually return before continuing. That's the trick. Because if G1 is calling G2 and G2 is calling G1, and G1 is calling G2 indefinitely, obviously the stack is growing, and at some point the stack is just exploding. But if G1 computes what it has to do later and then returns, then it can shrink the stack. Then G2 can start again, and again it will compute what to do later, return, which makes the stack to shrink again. And so you avoid the stack growing just unnecessarily. What we can do to achieve it is very simple. We just have a data type. That's very silly data type, actually, but it does the trick. We just say, okay, that's a thing. And say, okay, that's a function, just do it later. Just that, do it later. Obviously, we had to provide an interpreter to do, okay, but this is the representation of a computation. So what will you do later? If you have something that say, okay, do it later, you actually perform the computation. That's another do it later, and then you run it. The thing is, the interpreter is tail-rec. So it will work. So that's the trampolining thing. Before, instead of calling functions inside other function, you return a value. So you really return the value that represents what's to do next. And then because you're returning, the stack is shrinking, and then you can continue forever as long as your interpreter is stack safe. And obviously, here it is. So let's apply this new technique to what we have. And yeah, okay, that's just 3 slides. Okay. So Fibonacci final version. That's kind of complex, and that's technique involved. We have the CPS transformation, but what you see here is the mutual recursion is between Fibonacci, so fib-cd, and the interpreter. And the trampoline is just there. Just here, sorry. Just there. Because if we're calling in Fibonacci, we are calling the interpreter. So that we are calling call K. In call K, we were calling fib. And so we had a mutual recursion using the trampoline. When call K wants to call the Fibonacci function, actually it returns a value, the value of the type trompo, that says, yeah, that's not a result. What I want is to call Fibonacci. So that's jungling with the stack. And when you see that the function returns, just here, the call to K when it returns, the function says, okay, if the call to K is giving me a result, then that's a result. I give it back. But if the call to K is giving me the order to call myself on the argument N2 and K2, then I call myself. And this is all, almost. Because the problem is you can still have some of your function that is trapped here. F is trapped inside another function, fatmap, that we cannot rewrite, because what we did since the beginning was rewriting all the functions to make them into continuation Python style, then trying defunctionalizing, then to add trampolines. So we are modifying the code. It will be kind of complicated to ask the Zio developers or the CAS developers to modify the library to adapt for your specific cases. And clearly, we don't have time in 30 minutes to ask them that. So sometimes just trapped. So there, you're stuck. But luckily, most of these monads, because this is a problem that actually happens quite often, and the developers of these libraries are well aware of the situation, so they usually provide a very nice type class. And most of the IO monads implements this in a way or another. That's the differ type. And the differ says, okay, I have some computations to do just here. Please do the computation later. Please defer it, because if the call is done just right now, the stack will blow. So you will do it, but please later. And so if you have to call it into something like tail-recursive, for example, if your functor is or your monad is actually of the type class differ, then you can say, okay, call yourself, but please defer the call, so that tail-rec can return a value, and then the stack can shrink. A small trick, one of the last, is if you want to keep the tail-rec annotation, but your function is not tail-rec, and in some situation, like it's legitimate to have such a function, like with differ, like here the call is safe. Because of differ, it is gathered by differ, so it is safe. But of course, it's not tail-rec. So if you want to keep the compiler happy, what you can do is create another function, make it inline, and I call it f in disguise. That just calls f. But because it's another function, the compiler will not complain if you call it inside. That's a small trick, but it simplifies the life. Okay, so that's the end. And what to do next? So next, the next thing is there is a very nice option in the Scala compiler. It can generate intermediate language files, so very close to Java bytecode. And then you can ensure that actually you're not performing stack allocations. So that's if you want to activate this, just provide this flag, so the y_jnasmp and some dictionary, some folder, and then you can read. And what you should do is read the code, and to ensure that you're not calling, that all your calls are safe, and then all your code is really just a jump or something like that. I thank you very much for your attention. I wish you do not have the problem that we faced with the stack, and I hope it will help. These tips will help you in your everyday programming life. Thank you very much.
Thank you, Christophe. Thank you for sharing all these tips. That was really interesting. So we have one question from our audience coming from Pagoda 5B. And the question is, why not use free directly? And what are the pros and cons of writing the custom type classes?
A very nice question. Yeah, so if I go to the slides, yeah. Okay, there. I think that's the slide the most relevant to the question. The problem is the usual implementation of the free monad is having two constructs, like the pure, that is the same as here, and one representing flat map with impure. And the problem is we want in our structure to collect all the unitary calls. Our flat map is sequential, and the free monads ensure the sequentiality. And if we make all of our calls sequential and not parallel, then we cannot collect all the unitary calls, because we can only collect calls that are independent. Dependent calls, because maybe you call the API one time and the second call depends on the result on the first, then you can just not parallelize them because they're dependent. So the idea was to use more an applicative than a monad. And the free monad is made from really monads. I don't know if I really answered the question. I think it's really clear. But that's to maximize parallelism, and that's typically the way where you want an applicative more than a monad.
All right, thank you very much. Okay, it seems that was the last question, the only question. So thank you again, Christophe.